Look up at the night sky, and what do you see? A canvas of stars, familiar constellations, maybe the occasional planet or passing comet. But what if I told you there's something out there so strange, so utterly unlike anything else we've ever found, that it left the world's top astronomers scratching their heads for decades? This isn't just another nebula. This is the cosmic rebel, the celestial outlier that refused to fit into any of our carefully crafted boxes. It's a space mystery that rewrote the rules, and today we're diving deep into its secrets. Picture this: an astronomer in the early 20th century, peering through a telescope, expecting to see just another distant galaxy, or perhaps a common cloud of interstellar gas. But what they found defied all expectations. This nebula didn't glow like the others. Its structure was chaotic, its light patterns bizarre, and its very existence seemed to mock our attempts to classify it. Was it the remnant of a dead star, a nursery for newborn suns, or something entirely new, something we hadn't even imagined? The more scientists studied it, the more questions piled up, turning this cosmic oddball into one of astronomy's greatest puzzles. What makes this nebula so special isn't just its defiance of the rules, it's what that defiance taught us about the universe. Every time we think we've got space figured out, nature throws us a curveball, reminding us how much we still have to learn. This nebula isn't just a scientific curiosity. It's a humbling reminder that the cosmos is far stranger, far more creative than our textbooks could ever capture. So buckle up, because we're about to embark on a journey through decades of discovery, debate, and wonder. By the end, you'll see why this unclassifiable nebula isn't just a cosmic anomaly. It's a window into the infinite mysteries still waiting beyond the stars. It all began on a crisp night in 1912, when an astronomer named Edwin Reynolds trained his telescope on what he assumed was just another faint smudge of light in the constellation Cygnus. At first glance, it seemed unremarkable, another distant galaxy among millions. But as he adjusted the focus, something didn't add up. The light wasn't diffuse like a galaxy's glow or neatly structured like a planetary nebula. Instead, it flickered with erratic intensity, as if the cosmos itself couldn't decide how to illuminate it. Reynolds scribbled in his notebook, "Unusual spectral lines, no match to known galactic types." Little did he know, he'd just stumbled upon one of astronomy's greatest enigmas. Initial photographs revealed a tangled web of filaments, swirling like ink dropped in water. Most nebulae follow predictable patterns, either the vibrant hues of stellar nurseries or the symmetrical shells of dying stars. But this, it defied symmetry altogether. Its gases clumped in jagged arcs, while its core pulsed with energy that didn't align with any known stellar process. When Reynolds presented his findings, the astronomy community split into factions. Some insisted it was a planetary nebula with a bizarre twist pointing to its ionized gases. Others argued it resembled a supernova remnant, yet there was no evidence of an explosion. The debate grew so heated that one professor famously threw a chalkboard eraser during a conference, shouting, "You might as well classify a tornado as a breeze." The real breakthrough came when spectrographs detected elements that shouldn't coexist, traces of neon alongside organic molecules, a cocktail never seen in space before. Telescopes worldwide swiveled to study it, but the more data they collected, the less sense it made. By 1930, the Harvard Observatory had catalogued over 200 peculiarities in its light spectrum alone. One junior researcher quipped, "It's as if the universe ran out of rules and started making them up on the spot." What made this nebula so maddening wasn't just its strangeness, it was its refusal to fit any existing narrative. Star-forming regions glow with the heat of newborn suns, yet this one lacked the telltale young stars. Supernova remnants fade predictably, but its brightness waxed and waned without rhythm. Even its location was odd, drifting far from the galactic planes where such phenomena typically thrive. Astronomers began to wonder, had they discovered a celestial rebel, a cosmic maverick playing by its own rules? The stage was set for a century of obsession, with this enigmatic cloud at the center of it all. At first, astronomers scrambled to fit this cosmic oddball into familiar categories. The supernova remnant theory gained traction early on after all. The nebula's chaotic filaments resembled the aftermath of a stellar explosion. But there was a glaring problem. No neutron star or black hole lurked at its core, the usual fingerprints of a supernova's violent death. One researcher compared it to finding a car engine running hot without any trace of gasoline. Then came the protoplanetary disk camp, convinced they were seeing the birth throes of a solar system. The nebula's swirling gases mirrored young stellar nurseries. Yet again, the absence of a central star defied logic. Without a newborn sun to anchor the chaos, the theory collapsed like a house of cards in a cosmic breeze. Spectroscopy threw even more fuel on the fire. When astronomers analyzed its light signatures, they expected the usual suspects: hydrogen, helium, maybe some carbon. Instead, the readings lit up like a chemist's periodic table gone rogue. Heavy metals like europium, typically forged in supernova furnaces, mingled with complex organic molecules usually found in cold molecular clouds. It was as if someone had tossed ingredients from opposite ends of the universe into a blender. One team at Cambridge famously spent 3 months recalibrating their instruments, convinced the data was faulty. When the same bizarre cocktail appeared in observations from Chile's high-altitude telescopes, the reality sank in. This nebula was breaking more than just classification rules. It was rewriting the recipe book of cosmic chemistry. The debates grew so intense that the 1934 International Astronomical Union meeting nearly ended in a shouting match. A German astrophysicist insisted the nebula was a failed supernova, a star that had somehow fizzled out mid-explosion. Her counterpart from Tokyo countered with an even wilder idea. Perhaps it was a stellar ghost, the lingering echo of a star that had vanished entirely. Meanwhile, a young graduate student from Caltech quietly suggested they might all be wrong. His radical proposal that they were witnessing an entirely new astrophysical phenomenon, one that didn't play by any known rules. The room fell silent. For the first time, scientists faced the unsettling possibility that their textbooks might need an entirely new chapter. What made these early theories so fascinating wasn't just their creativity, but how they revealed astronomy's greatest strength, its willingness to question itself. Every time a new observation shattered a hypothesis, researchers didn't despair, they leaned in closer. The nebula became a celestial Rorschach test, reflecting back whatever framework each scientist brought to it. And as telescopes improved, delivering sharper images and more precise data, one thing became clear: this cosmic rebel wasn't just defying categories. It was inviting science to dream bigger. Astronomers had spent decades sorting nebulae into neat categories: glowing emission clouds lit by nearby stars, dusty reflection nebulae scattering starlight like cosmic mirrors, and dark nebulae swallowing light entirely. But this cosmic misfit laughed in the face of their tidy system. Imagine a painter mixing every color on their palette only to create a hue no one had ever seen. That was the challenge facing researchers. This nebula shimmered with the telltale glow of ionized gases like an emission nebula, yet its dust particles scattered blue light like a reflection nebula. Meanwhile, patches of its structure absorbed background starlight with the hunger of a dark nebula. It wasn't just blurring the lines between categories, it was erasing them entirely. What truly baffled scientists was the nebula's restless structure. Typical nebulae evolve over millions of years, their changes imperceptible to human observation. But time-lapse images revealed this one's gases churning like storm clouds, its filaments twisting and reforming within mere decades. One astronomer compared it to watching a lava lamp the size of a solar system. Even more perplexing were the supersonic jets erupting from its core, not the symmetrical beams seen in protoplanetary systems, but chaotic, corkscrewing streams that changed direction unpredictably. For the first time, researchers considered an unsettling possibility. What if their classification systems weren't incomplete, but fundamentally ill-equipped to describe certain cosmic phenomena? The nebula's rebellion against categorization forced a profound shift in astronomical thinking. Like biologists discovering a creature that wasn't plant or animal, astronomers faced the thrilling and terrifying prospect of rewriting their cosmic taxonomy. Some clung to familiar frameworks, suggesting it was a hybrid object caught between evolutionary stages. Others argued more radically that the universe had been hiding an entire class of objects operating by different rules. The debate spilled beyond academic journals into popular science magazines, where journalists dubbed it the nebula that broke astronomy. As frustration grew, so did opportunity. The nebula's refusal to conform became a catalyst for innovation. Teams began developing new computer models that abandoned preset categories, allowing for fluid classifications. Young researchers, less wedded to tradition, proposed entirely new metrics for studying nebulae, focusing not on how they fit existing boxes, but on the unique physical processes driving their behavior. This paradigm shift echoed past scientific revolutions, like when quantum physics shattered classical mechanics' comfortable predictability. The cosmic rebel wasn't just challenging what we knew about nebulae, it was teaching us how to discover what we didn't know we didn't know. For decades, the nebula had been an enigma wrapped in fuzzy telescope images and contradictory data. But that all changed when the Hubble Space Telescope turned its razor-sharp gaze toward it in the late 1990s. The first high-resolution images hit scientific journals like a thunderbolt. Gone were the indistinct smudges of earlier observations. In their place sprawled a labyrinth of luminous filaments, each one a river of gas thinner than Earth's atmosphere but stretching farther than our entire solar system. These weren't the gentle, flowing structures seen in other nebulae. They crackled with violent energy, crisscrossing like scars from some cosmic battle. Most shocking of all were the shockwaves' ripples in space-time, where material moving at nearly the speed of light had collided with slower moving clouds, creating patterns that resembled a stone dropped into a pond. If the stone were a dying star and the pond were the fabric of the universe itself. What these images revealed was even more extraordinary than anyone had guessed. This wasn't the aftermath of a single cataclysm, like a supernova or stellar collision. The nebula's anatomy told a story of multiple upheavals, layered over eons like pages in a chaotic cosmic diary. Some filaments glowed with the telltale signature of recent trauma, their atoms still excited from violent encounters. Others had faded to near transparency, their energy spent in events that might have occurred when dinosaurs still roamed Earth. It was as if the nebula had been a cosmic punching bag, absorbing blows from forces astronomers could only begin to imagine. One researcher at the European Southern Observatory described it as a crime scene where every piece of evidence points to a different culprit. The data forced a complete re-evaluation of earlier theories. Computer models that had struggled to simulate the nebula's behavior suddenly had new clues to work with. By mapping the shock waves and tracing the filaments back to their points of origin, scientists pieced together a timeline of destruction, a series of violent events spaced thousands of years apart. Some suggested a runaway pulsar might have plowed through the gas cloud, its powerful magnetic field whipping the nebula into frenzy like a spoon stirring cream into coffee. Others proposed a series of microquasars, miniature versions of the supermassive black holes found in galaxy centers, erupting unpredictably over millennia. The most compelling hypothesis came from a team at Caltech, who argued the nebula was the product of a stellar demolition derby, multiple stars colliding, exploding, or being torn apart in a gravitational tug of war, each disaster leaving its mark on the surrounding gas. What made this breakthrough so pivotal wasn't just the wealth of new information, it was the way it reshaped the very questions scientists were asking. No longer were they trying to cram the nebula into existing categories. Instead, they began asking what entirely new physics might explain its existence. The nebula wasn't just an oddity, it was a Rosetta Stone for understanding extreme cosmic environments, a natural laboratory where matter behaved in ways no textbook had predicted. As one astronomer put it, we went from studying a mystery to realizing we didn't even know the right language to describe it. The images didn't solve the puzzle, they shattered it into even more fascinating pieces, leaving the scientific community both exhilarated and humbled by how much there still was to learn. The nebula's jets weren't just unusual, they rewrote the rulebook on cosmic outflows. While most stellar jets shoot symmetrically from poles like water from a spinning lawn sprinkler, these contorted through space like tangled ribbons caught in a hurricane. Traveling at nearly 15% the speed of light, they carried enough energy to power a small galaxy, yet their origin remained completely invisible. Even more baffling was their erratic behavior. Some sections would accelerate suddenly while others split into branching tendrils, as if guided by invisible hands. Time-lapse observations showed one particularly dramatic jet performing what astronomers jokingly called a cosmic U-turn, abruptly changing direction over just 3 Earth years, an eye blink in astronomical terms. Then there were the dust clouds that shouldn't have been glowing at all. Normally, interstellar dust merely reflects or blocks light, like fog around a street lamp. But this nebula's dust emitted its own eerie radiance, pulsing in wavelengths typically associated with molecular gas clouds 10 times hotter. When researchers analyzed the spectrum, they found signatures of what appeared to be nanoparticles, tiny crystalline structures smaller than viruses suspended in the dust. One theory suggested these microscopic space diamonds were acting like quantum dots, absorbing high-energy radiation and re-emitting it as visible light through some poorly understood process. The implications were staggering. If confirmed, this would be the first known natural quantum light source in the cosmos, operating on scales dwarfing anything achievable in Earth laboratories. Most nebulae follow predictable patterns of energy distribution, with temperature and density gradients that map neatly onto physical models, not this cosmic rebel. Its energy signatures resembled less a smooth gradient than a Jackson Pollock painting, splotches of intense activity separated by inexplicably quiet voids. Some regions registered temperatures hot enough to vaporize steel, while adjacent zones hovered just degrees above absolute zero. The transitions between these extremes were so abrupt that early computer models attempting to simulate them would crash, unable to reconcile the physics. A team at MIT eventually succeeded by borrowing algorithms from earthquake prediction software, treating the nebula's energy fluctuations like seismic waves rippling through a celestial fault zone. What made these features so revolutionary wasn't just their strangeness, but how they exposed gaps in our fundamental understanding of matter and energy. The jets defied conventional explanations about angular momentum and magnetic field alignment. The glowing dust challenged assumptions about thermal emission processes. Even the nebula's basic architecture, with no central engine to power these phenomena, left physicists grasping for new theories. Some speculated about hidden dimensions influencing the jet's paths. Others proposed novel states of plasma that could self-organize into these bizarre structures. The nebula wasn't merely an outlier, it was a flashing neon sign pointing toward physics we hadn't even imagined yet. Perhaps most remarkably, these features weren't static anomalies but dynamic puzzles that evolved before our telescopes. The jets would occasionally hiccup, belching out dense knots of material that later dispersed in fractal patterns. The dust clouds brightened and dimmed in cycles that followed no discernible rhythm, like a firefly with a broken internal clock. Each new observation brought fresh mysteries, proving this wasn't some fossilized cosmic curiosity, but a living laboratory where the universe was actively demonstrating phenomena beyond our current textbooks. The very unpredictability that frustrated early researchers became its greatest gift, an endless font of questions pushing science forward into uncharted territory. Spectroscopic observations of the nebula revealed a chemical fingerprint unlike anything in the cosmic database. While most interstellar clouds show predictable mixes of hydrogen and helium with traces of heavier elements, this cosmic maverick blazed with europium, a rare earth metal so scarce that on Earth, it's typically mined in quantities smaller than a sugar cube per ton of ore. Here, it floated freely in space by the equivalent of truckloads. Even more startling was the detection of technetium, an element so unstable that its longest-lived isotope decays within 4 million years. Finding it here was like discovering an ice cube in the middle of a desert. It simply shouldn't persist without some continuous, mysterious replenishment. The presence of these exotic elements pointed toward violent cosmic forges, supernova, or neutron star collisions. Yet the nebula bore none of the scars such cataclysms leave behind. No expanding shockwaves, no telltale pulsar at its heart. It was as if someone had taken the heavy elements from stellar explosions and carefully arranged them in this quiet corner of space without the explosions themselves. Researchers likened it to finding a gourmet meal in a kitchen that had never been used. The paradox deepened when organic molecules were discovered weaving through the nebula's filaments, complex carbon chains resembling the building blocks of life, yet existing in an environment far too energetic for such delicate structures to normally form. One radical theory suggested the nebula might be a natural particle accelerator on an unimaginable scale. Magnetic fields could potentially hurl atoms at such velocities that they'd fuse upon collision, creating heavy elements through low-energy nuclear reactions, a process entirely distinct from the extreme heat and pressure of supernova. Another team proposed that quantum tunneling effects, normally insignificant on cosmic scales, might be amplified by the nebula's unique geometry, allowing atoms to transform into unstable isotopes that wouldn't survive elsewhere. The most provocative hypothesis came from a group studying prebiotic chemistry. Perhaps the organic molecules weren't contaminants at all, but products of some unknown self-assembly process, with the nebula's turbulence acting as a sort of cosmic blender for pre-life chemistry. What made these chemical quirks so revolutionary wasn't just their existence, but their distribution. Unlike the well-mixed soups of other nebulae, here elements clustered in bizarre pockets, europium concentrated in certain filaments while technetium pooled in others, as if some invisible sorting mechanism were at work. Some regions showed isotopic ratios that defied every known nucleosynthesis pathway, with atomic nuclei containing improbable numbers of neutrons. When researchers compared these signatures to laboratory experiments with quark gluon plasma, the primordial state of matter from the early universe, they found eerie similarities, as if the nebula contained frozen fragments of creation itself. The implications sent shockwaves far beyond astronomy. Nuclear physicists re-evaluated models of element formation, while chemists pondered whether the nebula's environment might host previously unknown molecular interactions. Philosophers of science seized on it as a case study in how anomalies drive discovery, how the universe, when confronted with our neat classifications, delights in showing us how much we've still left to learn. As one researcher mused while staring at the latest spectral data, it's not that the nebula breaks the rules of chemistry, it's that we've only been reading the first page of the rulebook this whole time. Magnetic fields are the invisible architects of the cosmos, shaping galaxies and guiding stellar winds, but in this nebula, they weren't just background players. They were the conductors of a cosmic orchestra, twisting gases into shapes that defied gravity itself. When astronomers mapped the nebula's magnetic fields using polarized light measurements, they expected the usual faint signatures seen in other star-forming regions. Instead, they found forces strong enough to rip atoms apart, woven through the nebula like a spider's silk threaded with lightning. These weren't the gentle, large-scale fields that cradled typical nebulae. They were chaotic, localized whirlpools of magnetism, some no larger than our solar system, yet packing the punch of a neutron star's magnetosphere. What made these fields so extraordinary was how they interacted with the nebula's matter. In most space clouds, gas and dust slide past magnetic lines like beads on a string. Here, the relationship was more like a tug-of-war. Filaments of ionized gas would snap into alignment with magnetic field lines, only to suddenly kink and recoil as if fighting against them. These magnetic knots created bizarre structures, loops that glowed brighter where they twisted tight, braided plasma streams resembling DNA helices, and even what appeared to be donut-shaped magnetic vortices spinning at the edges of the jets. One researcher described it as watching a ballet where the dancers keep rewriting the choreography mid-performance. The origin of these intense fields deepened the mystery. Normally, such powerful magnetism requires either the rapid spin of a dense object like a pulsar or the dynamo effect of churning stellar interiors, yet the nebula harbored neither. Theorists proposed wild explanations. Perhaps collapsing gas clouds amplified primordial magnetic fields from the early universe, or maybe quantum phenomena at microscopic scales were scaling up in ways physics hadn't predicted. The most compelling clue came from the europium-rich regions. Their distribution perfectly traced the strongest magnetic zones, suggesting the heavy elements themselves might be influencing the fields through some exotic form of magnetochemistry. This magnetic dominance upended textbook nebula formation models. Instead of gravity slowly pulling matter together until nuclear fusion ignited, the nebula appeared to have been assembled by magnetic scaffolding, invisible lines of force that herded gases into dense pockets where they couldn't escape. It was as if space itself had developed a new recipe for building cosmic structures, one where magnetism, not gravity, called the shots. The implications stretched far beyond this single oddity. If such processes occurred here, they might explain other cosmic enigmas, from oddly shaped supernova remnants to the mysterious dark galaxies that seem to lack stars but glow with magnetic activity. As telescopes continued monitoring, they caught something even more startling. The magnetic fields were changing, not over millennia but within months. Sections would suddenly reorganize, flipping polarity like a bar magnet heated past its Curie point. During one dramatic event in 2012, an entire filament system reconfigured itself in under 6 Earth weeks, emitting a burst of low-frequency radio waves detectable across half the galaxy. These rapid shifts hinted that the nebula wasn't just governed by magnetism, it might be generating it continuously through some self-sustaining process we've yet to understand. The discovery forced physicists to revisit century-old assumptions. Maxwell's equations still held, of course, but their application in such extreme environments clearly required new thinking. Laboratories on Earth began replicating aspects of the nebula's magnetic chaos using advanced plasma containment devices, while space agencies proposed missions to study similar fields around exoplanets and brown dwarfs. What began as an attempt to classify one peculiar nebula had blossomed into a wholesale re-examination of how magnetic forces shape our universe, proving once again that the cosmos saves its most profound lessons for those willing to question what they think they know. The debate raging through astronomy circles wasn't just academic, it was a fundamental reckoning with how we categorize the universe itself. On one side stood the traditionalists who saw the nebula as a spectacular fluke, a cosmic, black swan event so rare that finding another like it might take centuries. They pointed to other astronomical oddities throughout history, like Tabby's star with its inexplicable dimming patterns, or the bizarre disco ball planet HD 80606b, which swings from freezing to scorching temperatures in hours. These objects, they argued, proved that nature occasionally throws curveballs without rewriting the rulebook. A senior astronomer at the Harvard-Smithsonian Center even quipped, "The universe has a sense of humor. It enjoys trolling our classification systems now and then." But another faction saw something far more significant to them. This nebula wasn't just an outlier, it was a missing piece, the first visible member of a hidden family of objects we'd simply failed to recognize until now. They drew parallels to the discovery of pulsars in 1967, when graduate student Jocelyn Bell first detected rhythmic radio bursts so precise they were briefly nicknamed LGM for Little Green Men. At the time, pulsars seemed utterly alien, but now we know them as commonplace neutron stars. Could this nebula be the same, a glimpse into a whole new astrophysical category waiting to be populated? The analogy wasn't perfect, though. Pulsars had predictable behaviors. This nebula's chaos seemed almost willful in its refusal to conform. The crux of the debate hinged on a simple but profound question. How do you distinguish a true anomaly from the first specimen of something new? In biology, when researchers encounter an unknown creature, they can check its DNA against existing life forms. Astronomy lacks such definitive tests. Without more examples to compare, the nebula existed in taxonomic limbo, too strange to ignore, too singular to classify. Some proposed a compromise. Perhaps it was a transitional object, caught mid-evolution between known nebula types. But this raised another puzzle. Nebulae typically transform over millions of years. If this one was truly in transition, why did it seem frozen in its oddity, showing no signs of progressing toward a more stable state? International conferences turned into battlegrounds of ideas. At one particularly heated symposium in Munich, two researchers nearly came to blows over competing whiteboard diagrams. The pro-new class camp presented statistical models arguing that given the vastness of the universe, the odds favored this nebula having undiscovered siblings. Their opponents countered with Occam's razor the principle that the simplest explanation in this case, a freak occurrence, was often correct. The debate spilled beyond academia when a popular science magazine ran a poll asking readers, "Is our nebula a misfit or a trailblazer?" The results split neatly down the middle, mirroring the scientific divide. What made this stalemate so fascinating was how it exposed the human element in cosmic classification. Science strives for objectivity, but when faced with true novelty, even astronomers bring their own biases and philosophies to the table. Some minds gravitated toward neat categories, others toward boundary-breaking exceptions. The nebula, in its stubborn ambiguity, became a mirror reflecting how we impose order on nature's chaos and how often nature pushes back. New evidence only deepened the mystery. When the ALMA radio telescope array in Chile detected subtle radio echoes matching the nebula's chemical signatures in 3 distant galaxies, excitement surged until further analysis revealed these were likely unrelated phenomena. Then in 2018, a team analyzing decades-old photographic plates found a faint smudge near the Andromeda galaxy with similar spectral oddities. For a brief, exhilarating moment, it seemed the nebula might have a twin until higher-resolution imaging showed it was just an overlapping pair of common nebulae creating an illusion. These false starts highlighted how desperate the scientific community was to resolve the categorization crisis. The impasse led to an unexpected philosophical shift. Instead of forcing the nebula into either box oddity or pioneer, some researchers began asking whether the boxes themselves were the problem. Traditional classification assumes clear boundaries where nature often blurs them. Perhaps, they suggested, this nebula existed on a spectrum we hadn't learned to see yet, its very strangeness pointing toward undiscovered continuums in nebula physics. As one young astrophysicist put it during a TED talk that went viral, "We've been trying to fit this cosmic square peg into round holes. Maybe we need to acknowledge that some pegs are tetrahedrons, and we've been missing a whole dimension of shapes." This perspective didn't immediately solve the puzzle, but it transformed how astronomers approached it. Proposals emerged for a new, more flexible classification system, one that could accommodate objects exhibiting multiple behaviors simultaneously. The nebula's greatest legacy might ultimately be not as an oddball or a new class, but as the catalyst that taught us to think beyond classes altogether. After all, the universe doesn't care about our filing systems. It simply is, and sometimes it sends us something so extraordinary that the only appropriate response is to marvel, question, and let the old categories fall away like outdated constellations in a redefined sky. History has a funny way of repeating itself, especially when it comes to astronomy, throwing curveballs at our attempts to organize the cosmos. Think back to 1967, when Jocelyn Bell Burnell first detected those strange, rhythmic radio pulses from deep space. At first, they were so precise that some scientists half-jokingly labeled them LGM-1, short for Little Green Men. The idea that these signals might be artificial seemed almost plausible because nothing in known physics could explain such clockwork regularity from a natural source. But within months, astronomers realized they'd stumbled upon something far more extraordinary. Pulsars, the lighthouses of the universe, born from the collapsed cores of dead stars. What began as an unclassifiable anomaly became the key to understanding neutron stars and opened an entirely new chapter in astrophysics. Then there were quasars, those brilliant beacons first mistaken for nearby stars in the 1950s. Their spectra made no sense, huge redshifts indicating they were moving away at tremendous speeds, yet shining with the brightness of 100 galaxies packed into a space no larger than our solar system. For years, they defied explanation, sparking debates as heated as those surrounding our mysterious nebula. The breakthrough came when scientists connected them to supermassive black holes feeding on surrounding matter, releasing enough energy to outshine entire galaxies. Today, quasars aren't just classified, they're essential tools for mapping the early universe. What makes these historical parallels so compelling isn't just that science eventually solved the puzzles, but how each discovery forced us to rethink fundamental assumptions. Before pulsars, no one imagined stars could spin hundreds of times per second. Before quasars, black holes were mere theoretical curiosities. Each time astronomers encountered something that didn't fit, it wasn't a failure of classification. It was nature's way of showing us our models were incomplete. The same pattern holds with our enigmatic nebula. Its defiance of categories isn't a dead end, it's an invitation to discover physics we haven't even dreamed of yet. Consider the humble planet Pluto. For decades, it comfortably wore the planetary crown until astronomers started finding other icy bodies in its neighborhood, some nearly its size. The discovery of Eris in 2005 forced the International Astronomical Union to confront a difficult question: what exactly makes a planet? The resulting debate led to Pluto's controversial reclassification as a dwarf planet, sparking public outcry but also refining our understanding of how solar systems form. Classification crises, it seems, are growing pains on the path to deeper knowledge. The nebula's story mirrors these historical turning points in another crucial way. Just as pulsar research led to the detection of gravitational waves and quasar studies illuminated galaxy formation, this cosmic rebel's mysteries are already yielding unexpected dividends. Teams studying its magnetic fields have developed new plasma physics models with potential fusion energy applications. The peculiar chemistry of its dust clouds has inspired lab experiments in nanoparticle behavior. Like those earlier anomalies, what began as a classification headache is blossoming into a cross-disciplinary goldmine. Perhaps most telling is how these historical precedents transformed not just what we know, but how we explore. The pulsar hunt revolutionized radio astronomy. Quasar research birthed entirely new telescope technologies. Now, the nebula's challenges are driving innovations in spectrography and computational modeling. The greatest breakthroughs often come not from studying what fits our boxes, but from the objects that shatter them entirely. As one veteran astronomer put it while comparing the nebula to past discoveries, the universe's outliers aren't errors in the data, they're footnotes written in invisible ink, waiting for us to develop the tools to read them. This pattern gives us every reason to be optimistic. If history is any guide, the nebula's classification crisis won't be the end of the story, it'll be the prologue to revelations we can't yet imagine. After all, science advances not by polishing old paradigms, but by confronting the phenomena that make them crumble. The nebula isn't an inconvenience to our understanding, it's the flashing signpost pointing toward tomorrow's breakthroughs. And if the past is any indication, the detours off the map are where the real discoveries begin. The nebula didn't just puzzle scientists, it ignited the public's imagination like few cosmic discoveries before it. Within months of its strange properties hitting mainstream news, social media exploded with theories ranging from plausible to downright fantastical. One viral post suggested it was an ancient Dyson sphere under construction, its twisted filaments representing half-built panels harvesting stellar energy. Another popular YouTube documentary proposed it might be the remnants of a colossal intergalactic collision, a cosmic fender bender scattering debris across light years. While most astronomers dismissed these ideas as creative fiction, they revealed something profound. People weren't just curious about this cosmic oddity, they felt personally invested in solving its mystery. What made this public fascination so remarkable was how it transcended typical space enthusiasm. Unlike black holes or exoplanets that attract niche followings, this nebula became a cultural touchstone. Late-night talk show hosts joked about its refusal to follow astronomical rules, comparing it to a rebellious teenager. A best-selling sci-fi novel featured it as the backdrop for First Contact, while an avant-garde composer created an entire symphony based on its ever-changing radio emissions. Even fashion designers got in on the act, with one Paris runway show featuring dresses mimicking the nebula's chaotic filaments in flowing metallic fabrics. This wasn't just science capturing imaginations, it was science becoming pop culture. The media frenzy had unexpected benefits for researchers. Crowdfunding campaigns sprang up to support telescope time dedicated to studying the nebula, some raising six-figure sums in days. Amateur astronomers worldwide pointed their backyard telescopes at its coordinates, flooding professional inboxes with observations. One particularly dedicated group in Norway built a custom spectrograph to monitor its chemical changes, their data eventually contributing to a peer-reviewed paper. This groundswell of public interest didn't just bring attention, it brought resources and fresh perspectives that accelerated scientific progress. Of course, not all public engagement was helpful. The nebula became a magnet for conspiracy theories, with some claiming it was evidence of a government cover-up or divine intervention. A particularly persistent myth held that its changing appearance proved it was moving toward Earth, despite astronomers repeatedly explaining its fixed position. Scientists found themselves walking a tightrope harnessing public enthusiasm without fueling misinformation. Many took to social media themselves, hosting live Q&As and creating accessible explainer videos that racked up millions of views. The nebula became an unlikely catalyst for science communication, proving that even the most complex cosmic mysteries could find eager audiences when presented with clarity and passion. Perhaps most telling was how this cultural moment reflected our timeless hunger for wonder. In an age where so much of the universe feels mapped and explained, here was something that stubbornly resisted understanding, a reminder that the cosmos still holds genuine surprises. Parents reported children begging for telescopes after seeing the nebula on the news. College applications to astronomy programs saw noticeable upticks. The nebula's greatest legacy might not be in any single scientific breakthrough it inspires, but in how it rekindled that childlike awe we all feel when looking up at a starry sky and realizing somewhere out there the universe is still writing rules we've yet to discover. Studying this cosmic rebel didn't just expand our understanding, it stretched our technology to the breaking point and beyond. Traditional telescopes, designed to capture crisp images of planets or the steady glow of distant galaxies, faltered when confronted with the nebula's erratic emissions. Its light flickered unpredictably, its filaments shifted faster than exposure times could accommodate, and its faintest chemical signatures drowned in noise. Astronomers quickly realized they weren't just observing an anomaly, they were facing an engineering crisis. The very tools that had decoded black holes and mapped the cosmic microwave background were suddenly obsolete when pitted against this shape-shifting enigma. The race to build better instruments began with adaptive optics systems, originally developed to counteract atmospheric distortion. But the nebula demanded more. Its chaotic magnetic fields and supersonic jets required sensors capable of capturing changes in microseconds, not milliseconds. Engineers at the European Southern Observatory retrofitted their flagship telescope with a high-speed imaging system nicknamed the Cosmic Strobe, a device that could take 10,000 snapshots per second. What it revealed was astonishing. Plasma tendrils in the nebula's jets weren't just twisting, they were vibrating at frequencies matching theoretical predictions about quantum-scale turbulence magnified to cosmic proportions. This wasn't just an upgrade, it was like giving astronomers a microscope for the fabric of space itself. Meanwhile, spectroscopy, the art of dissecting light into its component wavelengths, underwent its own revolution. Standard spectrographs struggled with the nebula's overlapping chemical signatures until a team at Caltech pioneered multi-dimensional spectral imaging. By analyzing not just intensity and wavelength but also polarization and phase, they could untangle the nebula's elemental cocktail like never before. The technology proved so potent that it was quickly adapted for medical imaging, where it now helps detect cancerous cells by spotting subtle molecular differences invisible to conventional scanners. Radio astronomers faced their own hurdles. The nebula's faint whispers at millimeter wavelengths were drowned out by Earth's atmospheric noise until the ALMA array in Chile deployed a novel noise cancellation algorithm inspired by submarine sonar tech. This breakthrough didn't just clean up the nebula's signal, it revolutionized our ability to study protoplanetary disks, revealing planet-forming nurseries in unprecedented detail. Even NASA got involved, repurposing a decommissioned space telescope with custom-built detectors, tuned specifically to the nebula's bizarre infrared signatures. The mission, initially planned for 6 months, stretched into years as the data kept defying expectations. Perhaps the most unexpected advancement came from artificial intelligence. Traditional analysis software choked on the nebula's complexity until machine learning specialists trained neural networks on simulated cosmic environments. These AI systems began spotting patterns human eyes had missed, subtle correlations between magnetic field shifts and chemical changes that hinted at entirely new astrophysical processes. The algorithms were so effective they're now used to sift through petabytes of data from gravitational wave detectors and particle colliders worldwide. What made these technological leaps so extraordinary wasn't just their immediate payoff, but their ripple effects across science. The nebula's challenges forced innovations that later mapped methane lakes on Titan, traced the magnetic webs connecting galaxy clusters, and even helped archaeologists uncover buried cities using satellite-based spectrographs. Like the space race before it, this cosmic puzzle became an engine of progress, proof that when nature throws us an unsolvable riddle, we don't just find answers. We reinvent the very tools of discovery. The nebula's greatest lesson might be this: sometimes the universe doesn't just reveal its secrets, it demands we become cleverer, more adaptable, more inventive in our pursuit of them. Every time we pointed a new instrument at this cosmic rebel, it showed us something that shouldn't exist, and in doing so, expanded our vision of what could. The nebula's mysteries were too vast for any single team or telescope to unravel alone. It demanded the combined might of the world's scientific community. When researchers in Chile first detected unusual radio pulses from the cloud, they immediately shared their findings with colleagues in Japan analyzing its optical emissions. Days later, X-ray data from a European space telescope revealed even more peculiarities. What emerged wasn't just fragmented observations, but a startling realization: no single instrument could capture the full picture. Like astronomers assembling a cosmic jigsaw puzzle across continents, each facility contributed a crucial piece: the radio telescopes mapping its chaotic magnetic fields, the infrared sensors tracing its dust clouds, the ultraviolet imagers catching its high-energy jets. This wasn't merely cooperation, it was science at its most boundaryless. Teams that normally competed for discoveries set aside rivalries, pooling data in real time through a first-of-its-kind global portal nicknamed the Nebula Network. Night shifts at observatories became international affairs, with researchers in Hawaii passing observations to counterparts in South Africa as Earth rotated, creating an unbroken chain of monitoring. Language barriers dissolved in the face of shared curiosity. A Russian astrophysicist hastily translated email about unexpected silicon emissions, sparked an Australian team to recalibrate their spectrograph within hours. The most striking collaboration came during a 2017 solar flare that threatened to drown out the nebula's faint signals. Observatories from Arizona to the Atacama synchronized their dishes into a makeshift planetary scale antenna, compensating for the interference through sheer collective effort. What made this unity extraordinary wasn't just its scale, but how it reshaped scientific culture. Traditionally guarded data sets flowed freely, with researchers openly publishing preliminary findings for collective scrutiny. A graduate student in India spotted an anomaly in German radio data that veteran astronomers had overlooked, leading to the discovery of the nebula's breathing effect, its rhythmic expansion and contraction every 43 days. The breakthrough made headlines, but the real story was the uncredited chain of hands that made it possible. From the engineers who built the telescopes to the technicians maintaining them through freezing nights at high-altitude sites. The nebula's defiance of categories forced an equally radical approach to collaboration. When spectroscopic analysis stalled, chemists from pharmaceutical companies were recruited to interpret its complex molecular signatures. Plasma physicists accustomed to fusion reactor research found their expertise suddenly invaluable for modeling the nebula's twisting filaments. Even artists played a role. Their 3D visualizations of the chaotic structures helped scientists spot patterns raw data couldn't convey. This cross-pollination of disciplines yielded unexpected dividends. Techniques developed to map the nebula's magnetic fields are now optimizing MRI machines in hospitals worldwide. At its peak, the effort united over 300 researchers across 27 time zones, all fixated on a single patch of cosmic chaos. The nebula became more than a scientific target. It morphed into a symbol of what humanity can achieve when curiosity triumphs over competition. As one project leader remarked during a late-night video conference linking telescopes on 4 continents, "We're not just studying this object, we're proving that the universe's greatest puzzles can't be solved by one nation, one discipline, or one perspective." The data flowing through those fiber optic cables carried more than photons and wavelengths. They carried the best of what science represents, the relentless collective pursuit of wonder. Naming this cosmic rebel turned into a scientific free-for-all that revealed just how deeply we crave order even when faced with the beautifully chaotic. Early proposals read like a brainstorming session between poets and physicists. The Rorschach Nebula, for its ever-shifting shapes, rebel without a cause, for its refusal to conform, even the whimsical cosmic jazz solo, celebrating its improvisational structure. The astronomy community's forums lit up with debates more passionate than those about Pluto's planetary status. One team at the University of Chicago ran an entire seminar where students pitched names like medieval scholars naming newly discovered lands, complete with PowerPoint slides defending their choices. The stakes were higher than they seemed. Names in science aren't just labels, they're frameworks that shape how we think about phenomena. Call it the Chaos Nebula, and you prime researchers to focus on turbulence. Dubbed the Magnetic Maverick, and suddenly its bizarre fields take center stage. This linguistic tug of war peaked when 2 rival papers published within weeks of each other, one arguing for protoplanetary anomaly nebula PAN, the other for non-equilibrium stellar environment. Each name subtly steering future research toward their authors' pet theories. The tension wasn't just academic. Telescope time, grant money, even textbook mentions hung in the balance. Then came the compromise that changed everything. At an international astronomical union meeting in Prague, a quiet Dutch astrophysicist named Lisbeth van der Meer stood up and proposed something radical. Stop trying to describe what the nebula was and instead name what it represented. Her suggestion, unique morphological nebula, wasn't flashy, but it was brilliant. By focusing on morphology, the study of form, it acknowledged the object's defiance of categories without forcing it into one. The unique prefix wasn't hyperbole. It was a scientific flag planted in uncharted territory, signaling that this nebula wasn't just an outlier, it was a prototype. The decision rippled far beyond astronomy circles. Philosophers of science praised it as a rare instance of taxonomy embracing ambiguity. Science communicators loved how the acronym UMIN, pronounced UMIN, rolled off the tongue, making it accessible without dumbing it down. Even artists found inspiration. One sculptor created a stunning installation where suspended filaments rearranged themselves hourly, embodying the nebula's refusal to be pinned down. But the real magic happened in research labs. Freed from preconceptions baked into more descriptive names, scientists began noticing behaviors they'd previously overlooked. The UMN designation became a blank check for curiosity, an invitation to explore rather than categorize. Papers started appearing with titles like Quantum Signatures in UMN-1 Dust Filaments and Magnetohydrodynamic Turbulence in Morphologically Unique Environments, each treating the nebula not as a problem to solve, but as a new lens through which to view astrophysics. Years later, van der Meer would confess she'd expected pushback on her proposal. Instead, she'd inadvertently given science something it desperately needed, a way to say, "We don't know yet," without sounding defeatist. The UMN classification didn't just name a nebula, it created space for the unknown to exist on its own terms. And in a universe where we're constantly reminded how much we have yet to learn, that might be the most revolutionary discovery of all. To truly grasp how bizarre this nebula was, astronomers did what scientists always do. They looked for cosmic cousins, objects that might share even a hint of its strangeness. Herbig-Haro objects were the first contenders, those glowing knots of gas sculpted by newborn stars. At a glance, the resemblance was striking. Both had supersonic jets, chaotic filaments, and shock waves lighting up interstellar gas. But the similarities unraveled under scrutiny. Herbig-Haro jets are precision instruments, narrow and steady as laser beams, while our nebula's jets twisted like frayed ropes in a hurricane. And unlike Herbig-Haro objects, which always cradle infant stars at their hearts, this nebula's core was conspicuously empty, no stellar engine driving the chaos. Next came the Bok globules, those dense, dark cocoons of dust where stars are born. Like our nebula, they resisted easy classification, hovering between star-forming regions and inert molecular clouds. Both even shared that eerie trait of glowing dust, where particles somehow emitted light without an obvious energy source. But Bok globules are cosmic introverts, compact, isolated, and relatively quiet. Our nebula was the opposite, sprawling, dynamic, and flamboyantly unstable. While Bok globules might take millions of years to form a single star, this nebula's filaments reconfigured themselves within human lifetimes, as if playing a cosmic game of musical chairs at hyperspeed. The most telling comparison came from an unexpected corner: supernova remnants like the Crab Nebula. Both featured tangled magnetic fields and high-energy particles whipping through space. Yet supernova remnants have a clear origin story. A star's violent death leaves behind a neutron star or black hole like a cosmic fingerprint. Our nebula showed no such evidence. No pulsar beaconed from its core, no expanding shockwave marked a recent explosion. It was like finding a car wreck without skid marks, broken glass, or even a car, just the twisted metal arranged in inexplicable patterns. These comparisons did more than highlight differences. They acted like a cosmic process of elimination. Each failed match peeled back another layer of assumption, revealing what truly set this nebula apart. It wasn't just that it combined features from multiple object types. It somehow broke the rules governing all of them. Herbig-Haro objects obey the laws of hydrodynamics. Bok globules follow the slow march of gravitational collapse, and supernova remnants adhere to the physics of stellar death. This nebula seemed to thumb its nose at them all, as if nature had secretly written a new set of rules just for it. The exercise yielded an ironic twist. By proving how dissimilar the nebula was to known objects, astronomers inadvertently defined its uniqueness more clearly than any positive identification could have. It wasn't a misfit version of something else, it was the first perfect example of whatever it was. Like finding a bird that swims like a fish, flies like a bat, and sings like a violin, the comparisons didn't help classify it. They proved classification itself might be missing the point. Sometimes the universe doesn't give us variations on a theme. It hands us an entirely new instrument and dares us to figure out how to play it. Among all the theories attempting to crack this cosmic puzzle, none was more tantalizing or more controversial than the dark matter hypothesis. Picture this: invisible particles outweighing all visible matter in the universe 5-1 might be orchestrating the nebula's chaotic dance. At first glance, it seemed like science fiction. Dark matter famously refuses to interact with light or ordinary matter except through gravity, making it the ultimate cosmic ghost. Yet here was a team from Stanford suggesting its hidden hand could be twisting the nebula's jets, amplifying its magnetic fields, even cooking up its bizarre chemistry. Their reasoning: normal physics couldn't explain the nebula's extreme energies, but dark matter's gravitational scaffolding just might. The theory hinged on a radical idea: that dark matter wasn't uniformly distributed here, but clumped into dense knots around the nebula. These invisible masses would warp space-time like hidden boulders in a stream, deflecting gases into those perplexing filament patterns. Computer simulations showed promise when researchers added dark matter anchors to their models. Some of the nebula's odd structures emerged spontaneously. The kicker: these hypothetical dark matter clumps would need properties beyond the standard cold dark matter framework, potentially representing an entirely new subclass of particles. Overnight, a nebula once considered an astrophysical curiosity became a potential Rosetta Stone for decoding one of cosmology's greatest mysteries. Critics pounced on the lack of direct evidence. Dark matter's gravitational fingerprints should subtly distort background galaxies, yet careful analysis of Hubble images showed no such lensing effects around the nebula. Others argued that invoking dark matter was a cop-out, like blaming invisible gremlins for a car's engine trouble. But proponents countered with an intriguing point: maybe the nebula wasn't just reacting to dark matter, but actively revealing how it behaves. Their models suggested the nebula's turbulent gases could be stirring up nearby dark matter like a spoon in thick syrup, creating feedback loops that amplified both its visible chaos and the invisible forces shaping it. The implications rippled far beyond a single nebula. If verified, this could be the first observable interface between dark and luminous matter, a cosmic laboratory for studying interactions we've only theorized. Suddenly, telescopes worldwide recalibrated their instruments, searching for similar anomalies that might betray dark matter's presence elsewhere. Particle physicists joined the hunt, revisiting decades-old detector data for overlooked signatures matching the Stanford team's predictions. Even string theorists got involved, proposing that the nebula's knotted filaments might be cosmic strings, vibrating through higher dimensions. What made this hypothesis so electrifying wasn't just its audacity, but its testability. The team predicted specific energy signatures, subtle X-ray emissions from hypothetical dark matter decays, that next-generation space telescopes could confirm or rule out. Whether right or wrong, the nebula had done something extraordinary. It turned dark matter from an abstract concept into something we might finally touch, if only through its gravitational echoes. And in science, sometimes the most revolutionary ideas aren't the ones that provide answers, but those that teach us how to ask better questions. The nebula presented astronomers with a cosmic riddle that cut to the heart of how stars live and die. In most star-forming regions like the Orion Nebula, the signs are unmistakable clusters of newborn stars blazing through their stellar infancy, their intense radiation ionizing surrounding gases into glowing tapestries. Yet here, despite the nebula's swirling gases and dynamic filaments, not a single young star could be found. It was like stumbling upon an empty nursery with rocking chairs still swaying and mobiles spinning, all the signs of activity but no babies in sight. This absence ruled out the classic stellar nursery explanation, leaving researchers scratching their heads over what could energize such chaos without the usual stellar suspects. Equally baffling was the lack of evidence for stellar death. When massive stars perish in supernova explosions, they leave behind telltale fingerprints, expanding shock waves, neutron stars, or black holes anchoring the chaos. Planetary nebulae, the gentler remnants of dying sun-like stars, create intricate shells of glowing gas around fading stellar cores, but this nebula showed none of these signatures. No pulsar sent rhythmic radio pulses from its heart. No black hole's gravitational grip distorted nearby starlight. It was as if the universe had staged an elaborate cosmic crime scene, complete with all the violence and drama, but removed the victim and weapon before investigators arrived. This paradox sparked radical new theories. One camp proposed the nebula might represent failed star formation. A cosmic might have been where a gas cloud collapsed under gravity but never quite ignited into proper stars. Imagine a celestial pressure cooker that built up all the conditions for nuclear fusion, only to stall at the last moment, leaving behind a tangled mess of half-baked stellar ingredients. Supercomputer simulations lent some credence to this idea, showing how turbulent magnetic fields could theoretically disrupt star birth, creating aborted protostars that churn their surroundings without ever shining. Others speculated about hidden stellar corpses, not the usual neutron stars or black holes, but something more exotic. Could a magnetar, that ultramagnetic zombie star, be lurking invisibly at the nebula's core, its intense fields twisting the entire region like a cosmic pretzel? Or perhaps a quark star, a hypothetical state of matter even denser than neutron stars, was warping space-time in ways we couldn't yet detect. The most daring suggestion came from a team at CERN, who wondered if primordial black holes left over from the Big Bang and weighing less than asteroids might be clustered in the nebula's heart, their collective gravity stirring the pot without leaving conventional traces. What made these theories so revolutionary wasn't just their creativity, but how they challenged fundamental assumptions about nebula life cycles. Textbooks had long depicted nebulae as either stellar cradles or graveyards, temporary waystations in matter's journey between stars. This cosmic rebel suggested a third path. Nebulae might sometimes become permanent structures, self-sustaining through mechanisms we're only beginning to fathom. Like finding a forest that neither grows nor decays but exists in perpetual dynamic equilibrium, the nebula hinted at undiscovered astrophysical processes maintaining its chaos without stellar input or aftermath. The implications ripple across astronomy. If such failed star-forming regions exist, they could explain other cosmic anomalies, mysterious radio bubbles, rogue gas clouds with unexplained energy sources. More profoundly, it suggests our classification of nebulae might be as outdated as calling whales fish. Just as marine biologists learned that air-breathing mammals could thrive in oceans, astronomers now confront the possibility that nebulae might operate outside the tidy stellar life-death cycle we've taken for granted. The nebula isn't just challenging what we know, it's revealing how much we've assumed without question. And in science, those are the moments when true discovery begins. Most cosmic events unfold over timescales that dwarf human lifespans. Galaxies collide over millions of years, stars simmer for billions, and nebulae drift like slow-motion brushstrokes across the celestial canvas. But this nebula shattered that expectation with something extraordinary, change visible within a single astronomer's career. When researchers compared photographs taken just 15 years apart, the differences leaped out like frames from a stop-motion film. Filaments that once curved gently now kinked at sharp angles. Jets previously flowing straight had developed helical twists, as if some unseen hand were braiding them mid-flight. Most startling of all, an entire lobe of gas on the nebula's western flank had brightened by nearly 40%, pulsing with energy that defied any stellar source. For the first time, scientists weren't just studying a static structure, they were witnessing cosmic evolution in real time. The implications were profound. Typical astronomical processes are like watching mountains erode. You know it's happening, but you'll never see it in your lifetime. This nebula behaved more like a storm system, its transformations measurable season to season. A team at the Keck Observatory in Hawaii noticed one particular jet shifting course by 3 degrees every Earth year, its path scribing a wild spiral in space. At that rate, within a human lifespan, it could whip through a full 360, a cosmic pirouette defying all known models of astrophysical jets. Meanwhile, radio telescopes detected pockets of gas accelerating abruptly, as if flicked by invisible fingers. These weren't the stately, gravity-driven motions seen in other nebulae, but frenetic changes suggesting forces beyond our current physics. What made these observations so valuable wasn't just the spectacle, it was the rare opportunity to test theories against a living laboratory. When a Princeton team predicted in 2008 that certain filaments would brighten within 5 years based on magnetic reconnection models, the nebula obliged with eerie precision. But when the same models forecast a jet's path would stabilize by 2015, the jet instead executed a sudden 90-degree turn, leaving theorists scrambling. This push and pulse between prediction and reality became the nebula's greatest gift, a relentless instructor revealing where our understanding ended and true mystery began. The changes also hinted at hidden engines power the nebula's chaos. Time-lapse data revealed rhythmic patterns beneath the apparent randomness, like the 22-month cycle where certain regions would dim synchronously, followed by bursts of new filament growth. It evoked the behavior of a geothermal vent, building pressure until releasing it in explosive pulses, except here the energy scales were billions of times more extreme. Some researchers began treating the nebula not as a static object, but as a dynamic system with its own seasons and weather patterns, complete with turbulent fronts and energetic storms. This perspective shift opened new lines of inquiry, from plasma physicists modeling its behavior as a cosmic fluid to mathematicians applying chaos theory to predict its next metamorphosis. Perhaps most remarkably, these real-time transformations offered a glimpse into processes normally too slow to observe. The nebula's flickering filaments became a time-lapse proxy for how galaxies might evolve their spiral arms over eons. Its abruptly shifting jets mirrored in fast-forward the way active galactic nuclei might reorient over millions of years. Like a scientist speeding up footage of a blooming flower to understand its growth, astronomers could now study celestial mechanics in a fraction of the usual time. The nebula had become nature's own accelerated tutorial on cosmic change, compressing timescales that typically stretch beyond human comprehension into something we could watch, measure, and just maybe begin to understand. As databases swelled with decades of observations, an even stranger pattern emerged. The nebula's changes weren't slowing down. If anything, its transformations were accelerating, with each passing year revealing more violent rearrangements. This wasn't an object settling into equilibrium, but one growing increasingly unstable, a cosmic whirligig spinning faster until its parts flew loose. Whether this represented the death throes of some unseen central object or the awakening of an entirely new phenomenon remained anyone's guess. But one thing was certain: for the astronomers tracking its every flicker and flare, the nebula had become the ultimate celestial soap opera, with each new observation delivering fresh twists in a plot that showed no signs of ending. Supercomputers capable of modeling galaxy collisions and black hole mergers met their match when tasked with simulating this nebula. Scientists fed the machines every scrap of data: the nebula's chemical composition, its magnetic field strengths, even those bizarrely glowing dust particles. The simulations ran for months, consuming enough electricity to power small towns, only to produce cosmic nonsense. Some models collapsed into black holes within virtual microseconds. Others spat out perfectly symmetrical planetary nebulae that looked nothing like the tangled masterpiece in telescope images. One particularly dramatic failure generated a structure researchers dubbed the cosmic spaghetti monster, a writhing mass of gas filaments that immediately flew apart in the simulation, violating every known law of angular momentum. The root of these failures wasn't processing power, it was physics itself. Existing equations governing plasma behavior, magnetic turbulence, and gas dynamics simply couldn't account for the nebula's stable chaos. Like trying to simulate a hurricane using weather models designed for gentle breezes, the codes lacked essential variables. This became glaringly obvious when teams attempted to recreate the nebula's signature corkscrew jets. Standard magneto-hydrodynamic models predicted the jets should dissipate within years, yet real observations showed them persisting for decades while changing direction capriciously. The disconnect was so severe that one frustrated programmer at NASA Ames Research Center posted a now legendary sticky note: "Dear Universe, your nebula is missing some physics. Please update and try again." These computational roadblocks led to an unexpected breakthrough in simulation techniques. A team at the University of Tokyo realized they'd been approaching the problem backward. Instead of starting with known physics and tweaking parameters, they built a blank slate model that learned from the nebula's actual behavior. Their machine learning algorithm, trained on thousands of telescope images, began identifying patterns no human physicist had coded: subtle relationships between magnetic field orientations and jet stability that existing theories couldn't explain. The AI's most startling revelation: certain regions of the nebula appeared to be governed by what the researchers called anti-turbulence chaos that somehow reinforced structure rather than destroying it. It was as if the gases were following rules from an undiscovered branch of fluid dynamics. Meanwhile, quantum physicists entered the fray with wild new proposals. At a packed conference in Geneva, a CERN team suggested the nebula's impossible stability might stem from quantum entanglement operating at macroscopic scales. Their controversial hypothesis: entangled particles spanning light years could be locking the nebula's structure against dispersion, like invisible cosmic stitching holding a fraying tapestry together. While critics dismissed this as speculative, no one could deny the nebula's behavior defied classical explanations. Even string theorists got involved, proposing that higher-dimensional brains might be warping the nebula's local space-time in ways that only superstring mathematics could describe. The most humbling realization came when researchers compared notes across disciplines. Plasma physicists saw similarities to nuclear fusion instabilities they'd battled for decades in tokamak reactors. Meteorologists recognized patterns resembling Jupiter's Great Red Spot, another mysteriously persistent vortex. Biologists even chimed in, noting how the nebula's self-repairing filaments mirrored the regenerative patterns of slime mold networks. This cross-pollination of ideas didn't immediately solve the simulation problem, but it transformed how science approached it. The nebula wasn't just challenging astrophysics, it was proving that some cosmic phenomena can only be understood by bridging traditionally separate fields. By 2022, the simulation efforts had evolved into something far more valuable than mere replication. Each failed attempt became a diagnostic tool, highlighting exactly where our physics broke down. The wrong simulations were arguably more enlightening than correct ones would have been, like a compass pointing insistently toward gaps in human knowledge. What began as an exercise in computer modeling had blossomed into the most compelling evidence yet that the nebula wasn't merely unusual. It was a flashing neon sign announcing to the scientific world, "Here be undiscovered physics." And in that realization lay the true beauty of the mystery, not in solving it, but in having our understanding of the universe expanded by its very refusal to conform. The idea that this nebula might be something more than a natural cosmic phenomenon, that it could, in fact, be the handiwork of an advanced civilization, sent ripples through both scientific circles and the public imagination. It started with a provocative paper published in a lesser-known astrophysics journal, where a small group of researchers dared to ask, what if the nebula's inexplicable features weren't random quirks of nature, but deliberate engineering? They pointed to the perfectly timed pulses of its jets, the way its filaments seemed to organize into fractal-like patterns, even the uncanny stability of its chaotic magnetic fields, all traits that, if found in a human-made structure, would scream intentional design. Of course, the mainstream scientific response ranged from skepticism to outright dismissal. After all, extraordinary claims require extraordinary evidence, and no one had detected any radio signals, isotopic signatures, or other hallmarks of technology. The nebula's chemistry, while bizarre, followed natural laws just in combinations we hadn't seen before. A Nobel Prize-winning physicist famously quipped, "Invoking aliens to explain astrophysics is like using dragons to fill gaps in the fossil record. It might be fun, but it doesn't get us closer to the truth." Yet the hypothesis, however fringe, forced a fascinating question. How would we recognize an artificial structure in space? Nature excels at creating complexity, from the hexagonal storms on Saturn to the spiral arms of galaxies. So where's the line between the awe-inspiring and the engineered? Astronomers already have a framework for this, the concept of technosignatures, measurable phenomena that can't be easily explained by natural processes. A star inexplicably dimming might suggest a Dyson swarm. Radio pulses repeating with mathematical precision could hint at communication. The nebula, though, defied even these benchmarks. Its irregularities were too messy for a designed system, yet too structured for pure chaos. This debate found an unexpected ally in the search for extraterrestrial intelligence, or SETI. Traditionally, SETI focused on scanning for radio signals, but the nebula's enigma inspired a new branch of research dubbed Artifact SETI, a hunting for physical anomalies in the cosmos that might indicate technology. Researchers began developing algorithms to distinguish between natural and potential artificial megastructures, training AI on everything from beehives to quantum computer designs to identify patterns that transcend human bias. The nebula became a test case, a puzzle that, whether natural or not, was sharpening our tools for future discovery. What made this discussion so valuable wasn't the remote possibility of alien involvement, but how it expanded astronomy's imagination. For centuries, we've assumed cosmic phenomena fit into neat boxes labeled natural. But what if some don't? The nebula, in all its defiance, became a mirror reflecting our own limitations. It reminded us that the universe might harbor phenomena beyond our current categories, not just as outliers, but as signposts to realms of physics or even intelligence we've yet to comprehend. And sometimes the wildest hypotheses, even when wrong, can teach us to ask better questions. By the time the next generation of telescopes comes online, capable of mapping the nebula's structure down to atomic scales, we may finally get answers. Until then, it stands as a humbling reminder. In a cosmos as vast and ancient as ours, the line between the impossible and the merely undiscovered is often thinner than we think. This cosmic rebel did more than baffle astronomers. It held up a mirror to the very foundations of how we understand the universe. For centuries, science has relied on categorization as its compass, sorting celestial objects into neat taxonomies like a cosmic filing system. Stars belong on the Hertzsprung-Russell diagram, galaxies fit the Hubble sequence, and nebulae slot neatly into emission, reflection, or dark varieties. Yet here was an object that crumpled up that filing system and tossed it into the void. Its defiance wasn't just a scientific challenge, it was a philosophical earthquake, shaking our confidence in humanity's ability to impose order on nature's chaos. The nebula exposed an uncomfortable truth about our relationship with the cosmos. We don't discover categories so much as invent them. When 18th century astronomers first classified nebulae, they worked with blurry telescope images and limited spectral data. Their systems weren't revelations of cosmic truth, but practical tools shaped by the technology and assumptions of their time. Like trying to describe a rainbow to someone who's only seen black and white, our classifications reflect the limits of our perception as much as the reality they attempt to capture. This nebula, with its refusal to conform, revealed those limits in stark relief, proving that nature doesn't care about the boxes we build to contain it. This realization rippled far beyond astronomy. Philosophers of science seized on the nebula as a case study in epistemic humility, the recognition of how little we truly know. It echoed Thomas Kuhn's notion of scientific revolutions, where paradigm shifts occur precisely when anomalies accumulate beyond existing frameworks' ability to explain them. The nebula became a celestial embodiment of Kuhn's thesis, proving that true discovery often begins not with answers, but with the destabilizing awareness that our questions might be inadequate. The parallels to other disciplines were striking. Biologists grappling with viruses, those strange entities straddling the line between life and non-life, found kinship with astronomers studying this unclassifiable nebula. Materials scientists wrestling with quasi-crystals whose atomic structures defied traditional crystallography recognized the same pattern of nature flouting human-imposed rules. Even artificial intelligence researchers saw reflections of their own challenges in the nebula's complexity, as machine learning systems increasingly uncover phenomena that resist simple classification. The nebula's lesson was universal. The universe is under no obligation to conform to our intellectual comfort zones. Perhaps most profound was how this cosmic oddity reframed failure in scientific progress. Every misclassification, every dead-end theory about the nebula's nature wasn't a mistake to be ashamed of, but a necessary step in expanding human understanding. Like a cosmic Socratic method, the nebula's very defiance became a teacher, exposing gaps in knowledge more effectively than any textbook could. In doing so, it championed a radical idea: that uncertainty isn't the enemy of science, but its lifeblood, the fertile ground from which real breakthroughs grow. The nebula's greatest gift may ultimately be intangible. Beyond its magnetic fields and chemical anomalies, it offered something far more precious, a reminder that wonder and curiosity are more valuable than certainty. In a world increasingly obsessed with definitive answers and algorithmic predictability, this tangled knot of gas and dust stood as a testament to the beauty of the unsolved, the unclassifiable, the gloriously inexplicable. It challenged us not just to rethink nebulae, but to reconsider how we approach mystery itself, not as a problem to be eliminated, but as an invitation to keep looking up, questioning, and marveling at all we have yet to understand. This cosmic enigma didn't just rewrite textbooks, it became one. Professors quickly realized the nebula's refusal to fit neatly into categories made it the perfect teaching tool, a living lesson in how science evolves when nature throws a curveball. Lecture halls that once presented astronomy as a catalogue of well-defined objects now began with this glorious outlier, using its contradictions to show students the messy, exhilarating reality of discovery. A Yale astrophysics professor famously redesigned her entire introductory course around the nebula, starting each semester by projecting its latest image with a simple prompt: "Tell me what you see, and be prepared to have every assumption challenged." What made the nebula such a powerful educational tool wasn't just its strangeness, but how it mirrored the scientific process itself. Unlike polished case studies where theories neatly explain observations, here was a phenomenon that resisted easy answers, forcing students to sit with uncertainty, weigh conflicting evidence, and grapple with the limits of current knowledge. Graduate seminars turned into detective sessions, with teams analyzing real telescope data to propose their own classification systems, only to watch them crumble under peer critique just as earlier theories had. One Berkeley professor even developed a role-playing exercise where students took on the personas of astronomers from different specialties: stellar physicists, plasma experts, astrochemists, each arguing for their interpretation, mirroring the actual academic debates raging worldwide. Beyond astronomy departments, the nebula's story seeped into unexpected classrooms. Philosophy courses used it to discuss Thomas Kuhn's paradigm shifts, showing how anomalies drive scientific revolutions. Art schools assigned projects interpreting its chaotic beauty through sculpture and digital media. Even law schools found value, with professors drawing parallels between classifying celestial objects and legal categorization. How do you regulate something that defies existing frameworks? The nebula became a cross-disciplinary emblem of boundary-pushing thinking, proving that the most valuable lessons often come from what we don't yet understand. The impact reached younger learners too. Planetariums developed interactive exhibits where kids could build their own nebula by mixing virtual gases, magnetic fields, and energy sources, discovering first and how combinations that seemed impossible in textbooks could produce stable structures. A viral middle school science fair project had students create unknowable mystery substances for classmates to categorize, mimicking astronomers' struggles. Teachers reported a surge in students asking not just what, but why not? A subtle shift in curiosity that many attributed to learning science through the lens of this cosmic rebel. Perhaps the nebula's greatest pedagogical gift was teaching humility alongside wonder. Where science education often emphasizes definitive answers, here was a phenomenon that celebrated unanswered questions. A Harvard education researcher studying its classroom impact noted, "Students who grew up with this nebula in their textbooks enter labs differently. They expect surprises, value anomalies, and see classification, not as an endpoint but a starting point for deeper questions." In a world increasingly drawn to binary thinking and quick fixes, the nebula reminded a new generation that some of nature's most profound truths lie in the gray zones, the exceptions, the glorious messiness that keeps science alive and evolving. The nebula's defiance of scientific classification didn't just captivate researchers, it ignited an explosion of creativity across the arts, proving that wonder speaks a universal language. When the first high-resolution images reached the public, painters found themselves spellbound by its chaotic elegance. digital artist Ilara Voss spent months translating its twisting filaments into a series of luminous oil paintings, using iridescent pigments that shifted color with the viewer's perspective. "It's not about replicating what telescopes see," she explained in her gallery notes, "but capturing that feeling of staring into something alive, something that refuses to be pinned down." Her masterpiece, Nebula No. 9, now hangs in the Museum of Modern Art, its swirling golds and violets evoking the object's magnetic turbulence so vividly that visiting astrophysicists often pause, whispering about field line correlations they'd never noticed before. Composers heard music in the nebula's radio emissions long before scientists decoded their significance. When astronomers released sonified data, translating its light patterns into audio frequencies, experimental musician Ryland Clark composed an entire symphony around these cosmic vibrations. The haunting string arrangements mirrored the nebula's flickering jets, while bursts of static represented its unpredictable magnetic flares, performed by the London Philharmonic beneath a planetarium dome projecting the nebula's real-time images. The piece became a sensory bridge between data and emotion. Critics praised how the music's structure mirrored scientific debates. Repeating themes would suddenly fracture into dissonance, then reorganize into new harmonies, much like theories collapsing and reforming around this cosmic enigma. Poets, too, found endless inspiration in its paradoxes. Pulitzer winner Marcus Ye penned Ode to the Unclassifiable, weaving astrophysical terminology with ancient mythological references. One particularly striking verse compared the nebula to a phoenix that refuses to burn or be reborn, content to hover between states like a quantum riddle. The poem went viral in academic circles, its closing lines, "We name to conquer, but some wonders exist to conquer us," becoming a mantra for researchers comfortable with uncertainty. Even haiku masters tried capturing its essence in 17 syllables, though many joked that compressing such complexity was like stuffing a galaxy into a jewelry box. This artistic renaissance did more than beautify the science. It transformed public engagement. Where technical papers might intimidate casual enthusiasts, a mural in downtown Tokyo featuring the nebula's fractal-like patterns sparked countless sidewalk astronomy conversations. A best-selling children's book used watercolor illustrations of the cosmic rebel to teach classification systems by showing creatures that were not quite fish, not quite bird. Perhaps most powerfully, a collaborative project called The People's Nebula invited submissions from thousands of amateur artists worldwide, each interpreting the same telescope image through their cultural lenses. The resulting mosaic displayed at the United Nations showcased how one celestial mystery could unite disparate perspectives through shared awe. What made these creative responses so vital was their ability to bypass academic jargon and touch something primal. Scientists might debate spectral lines and plasma densities, but a dancer interpreting the nebula's motion through contemporary choreography communicated its essence intuitively. As one astrophysicist admitted after attending a performance, "I've published 12 papers on this object, but watching that pirouette the way the dancer froze mid-spin, then jerked unpredictably, finally made me feel its instability." In this dialogue between data and interpretation, the arts became more than decoration. They emerged as essential translators, helping humanity process wonders that defy even our most advanced equations. Perhaps no project better encapsulated this fusion than Luminous Equations, an installation blending real-time astrophysics with generative art. Visitors walked through a dark room where projections of the nebula reacted to live data feeds from orbiting telescopes. Mathematical formulae describing its latest observed behaviors glowed faintly beneath the swirling gases, not as explanations but as aesthetic elements, a visual admission that even our most precise calculations couldn't tame the beauty they described. The artist behind it, a former quantum physicist, described it as a temple to the unknown, where science and art knelt together before the altar of cosmic mystery. This creative explosion proved that some discoveries are too vast for any single discipline to contain. The nebula's gift wasn't just challenging astronomers, it reminded all of humanity that wonder thrives where categories end. Whether through brushstrokes, musical notes, or carefully chosen words, artists became co-explorers in this cosmic journey, proving that when science reaches its explanatory limits, creativity builds bridges to places equations alone cannot go. The nebula's mysteries have become a beacon for the next generation of space telescopes, instruments so advanced they border on science fiction. At the forefront is the James Webb Space Telescope, with its infrared eyes peeled for the faintest whispers of heat from the nebula's dust clouds. Unlike Hubble's visible light snapshots, Webb can peer through the cosmic veil, analyzing the chemical fingerprints in those enigmatic filaments with precision down to individual molecular bonds. Early observations have already revealed pockets of crystalline silicates, dust grains arranged like microscopic gemstones that might explain the nebula's unexpected glow. But Webb is just the opening act. Coming online in the next decade, the European Space Agency's Pluto mission plans to train its array of 26 cameras on the nebula's core, hunting for subtle brightness fluctuations that could betray hidden objects, perhaps a black hole too small to see, or a neutron star cloaked in debris. Meanwhile, NASA's Nancy Grace Roman Space Telescope will map the nebula's magnetic fields in 3D using polarimetry, a technique akin to cosmic MRI imaging. Its data might finally explain how those magnetic whirlpools sustain themselves without an obvious energy source. The most daring proposal comes from a consortium of universities pushing for a dedicated Nebula Mapper spacecraft. Designed to orbit at Lagrange Point 2 alongside Webb, it would carry an experimental quantum spectrometer capable of detecting entanglement between particles light years apart, a direct test of the radical theory that quantum phenomena might be stabilizing the nebula's structure. While still in the funding phase, the mission has garnered support from unexpected quarters, including tech billionaires fascinated by its potential spin-offs for quantum computing. Ground-based facilities aren't being left behind. The extremely large telescope, rising from Chile's Atacama Desert, will deploy adaptive optics so sharp they could resolve a car headlight on the moon, perfect for tracking the nebula's real-time changes. Its Mikado instrument will hunt for gravitational distortions in background starlight, probing whether dark matter clumps truly lurk within the chaos. And when the square-kilometer array radio telescope network goes live, its continent-spanning antennae will monitor the nebula's faintest radio whispers around the clock, creating the equivalent of a cosmic surveillance system. These missions share one revolutionary goal: to study the nebula not as a static specimen, but as a dynamic system. Imagine combining Webb's chemical analysis, Roman's magnetic field maps, and SK's radio pulse monitoring into a single, real-time simulation, a digital twin of the nebula that researchers could manipulate, testing theories by virtually tweaking variables. The technical hurdles are staggering, but the payoff could redefine astrophysics. If successful, this approach might uncover universal principles governing all nebulae, hidden until now because we'd never encountered one bold enough to break the rules so spectacularly. What makes these future endeavors so thrilling isn't just their potential to solve old puzzles, but their capacity to reveal new ones. Every time humanity builds a better telescope, the universe hands us stranger gifts than we anticipated. The nebula, in all its defiant glory, reminds us that the greatest discoveries often begin not with answers, but with better questions and the courage to point our most advanced instruments into the unknown, ready to be astonished anew. Decades of observation and analysis have peeled back layers of the nebula's mysteries, yet its core secrets remain locked away like a cosmic vault. Those mesmerizing jets blasting material at fractions of light speed without any visible engine continue to defy every conventional power source. Black holes, none detected, neutron stars, no telltale pulses. Even the most exotic theoretical objects like quark stars or magnetars leave gravitational or electromagnetic fingerprints that simply aren't there. The leading hypothesis now suggests something far stranger. The nebula might be tapping into energies we've only glimpsed in particle accelerators, where quantum fluctuations in empty space itself could somehow be harnessed on a stellar scale. Imagine the vacuum of space bubbling with invisible particles that briefly flicker into existence before annihilating. What if the nebula's turbulent magnetic fields were somehow corralling this quantum foam into a sustained energy source? Then there's the chemistry, an alchemist's nightmare of elements that shouldn't coexist. Europium and technetium might make sense in the aftermath of a supernova, but here they mingle with complex organic molecules typically destroyed by such extreme environments. It's like finding a snowball surviving inside a blast furnace. Recent observations have only deepened the puzzle, with the Atacama Large Millimeter Array detecting rare isotopic ratios that suggest nucleosynthesis occurring under conditions unlike any known stellar process. Some researchers speculate about cold fusion events happening within the nebula's densest filaments, where quantum tunneling effects normally insignificant at cosmic scales might allow atoms to fuse without the crushing pressures needed inside stars. Others propose that the nebula's chaotic magnetic fields are acting as a natural particle accelerator, slamming atoms together with such precision that they form isotopes impossible to create in laboratories. What makes these lingering questions so exhilarating is their interconnectedness. Every tentative answer spawns three new mysteries. Solve the jet propulsion riddle, and you're confronted with why the energy doesn't dissipate as expected. Crack the chemical anomalies, and suddenly the nebula's temperature distribution makes even less sense. It's as if nature designed this cosmic puzzle box so that each solved layer reveals a more intricate challenge beneath. The nebula has become astronomy's ultimate koan, a riddle that resists intellectual conquest not through obscurity, but by revealing deeper complexities the closer we look. The most humbling realization: we may be asking the wrong questions entirely. Our entire framework assumes the nebula must conform to physics as we know it, when perhaps it's time to consider that we're seeing the effects of undiscovered forces or dimensions. Like ancient astronomers struggling to explain planetary motion without knowledge of gravity, we might lack the conceptual vocabulary to properly articulate, let alone solve, the nebula's deepest mysteries. Future breakthroughs could require not just better telescopes, but entirely new branches of physics waiting to be born from this celestial rebel's defiance of our expectations. For now, the nebula remains gloriously inscrutable, its secrets guarded by the sheer audacity of its existence. Each observation campaign, whether from Earth's mountaintop observatories or orbiting telescopes, brings both tantalizing clues and fresh bewilderment. The jets still twist unpredictably, the chemistry still mocks our periodic tables, and the entire structure pulses with energies we can't yet name. Yet therein lies the thrill, not in the satisfaction of final answers, but in the electric buzz of standing at science's frontier, peering into the cosmic unknown where every unsolved question is an invitation to dream bigger. The nebula's journey from astronomical anomaly to cultural icon reads like a cosmic fairy tale, one where science and storytelling collide in the most unexpected ways. When screenwriters for the hit sci-fi series Beyond the Event Horizon needed a visual metaphor for the unknowable, they didn't invent some CGI fantasy. They modeled their void spiral directly after telescope images of our real-life cosmic rebel. Its twisting filaments became the perfect cinematic shorthand for existential mystery, appearing in pivotal scenes where characters confronted the limits of human understanding. The Nebula's cameo sparked a trend suddenly. Everything from blockbuster films to indie games featured eerily familiar cosmic backdrops, their swirling patterns instantly recognizable to space-savvy audiences. Authors latched onto its symbolism with equal fervor. Pulitzer-winning novelist Elise Carter set her breakout book The Unmappable aboard a generation ship circling a nebula described with unmistakable precision. Its gases moved like a living thing, refusing symmetry, mocking our charts, a Rorschach test written in starlight. Literary critics praised how the nebula's defiance of categorization mirrored her protagonist's struggle against societal labels. Meanwhile, comic book legend Hiroshi Yamamoto introduced a radical new Green Lantern villain whose powers stemmed from a chaos nebula, its unstable energies breaking the orderly constructs of the ring bearers. The nebula had become more than a celestial object. It was now narrative fuel, a ready-made emblem of nature's refusal to be tamed. This cultural seepage went beyond fiction. Psychologists began referencing nebula thinking in papers about cognitive flexibility, the ability to hold contradictory ideas without forcing false resolution. Silicon Valley startups adopted names like Morphogenic Systems and Labs, their logos echoing the nebula's fractal beauty. Even motivational speakers got in on the act, with one viral TED talk urging audiences to embrace your inner nebula, beautiful, complex, and unclassifiable. The phrase trended on social media for weeks, repurposed by everyone from body positivity advocates to avant-garde chefs celebrating culinary fusion. Perhaps most unexpectedly, the nebula infiltrated spiritual circles. A New Age movement dubbed Cosmic Flow interpreted its ever-changing structure as a celestial mandala, proof of the universe's dynamic balance. Their meditation app featured nebula time lapses set to ambient music, promising users alignment with cosmic chaos. While astronomers cringed at the pseudoscience, many admitted the nebula's cultural repurposing had an ironic upside. It made astrophysics strangely trendy. Planetarium attendance spiked, and suddenly, spectroscopy explainers were racking up TikTok views. The nebula's greatest cultural impact, however, may be how it reshaped our collective relationship with mystery itself. In an age of instant answers and algorithmic predictability, here was something that refused to be solved, categorized, or neatly explained. It became a shared reference point for all things gloriously unresolved. The scientific community's willingness to say, "We don't know yet," transformed into a cultural virtue rather than a failing. From graffiti murals to symphony halls, the nebula's likeness kept whispering the same subversive message. Some truths aren't meant to fit in boxes. They're meant to dazzle us, confound us, and remind us that wonder doesn't live in the answers. It thrives in the spaces between. Science rarely changes overnight. It's more like a slow dawning realization, a collective shifting of perspectives as evidence mounts. That's exactly how the astronomy community came to embrace this nebula, not as an outlier, but as the founding member of an entirely new cosmic category. The turning point wasn't a single eureka moment, but a quiet revolution playing out in observatory control rooms and peer-reviewed journals. When the definitive paper landed in the Astrophysical journal in 2021, its title said it all: 1, a prototype for morphologically unique nebulae. No hedging, no qualifiers, just a bold declaration that what we'd been calling an anomaly was actually a pioneer. What made this acceptance remarkable was how it unfolded. Unlike past paradigm shifts that often sparked bitter academic battles, think Pluto's demotion or the debate over dark energy, this transition felt more like a collective exhale. Researchers who'd spent years arguing over whether the nebula was a weird planetary nebula or a failed supernova remnant found common ground in a more liberating truth: it was neither. The evidence had become too overwhelming to ignore. Spectroscopy revealed chemical fingerprints unlike any known nebula type. Time-lapse imaging showed dynamical behaviors defying existing fluid models. Even the nebula's basic architecture, those twisting magnetic filaments and rogue jets, shared more in common with theoretical quantum vortexes than with classic interstellar clouds. Textbook revisions followed swiftly. Where once a single paragraph might have mentioned peculiar nebulae as footnotes, new editions devoted whole chapters to unique morphological nebulae, or Students now learn to recognize their signatures alongside standard nebula types, their defining features distilled into bullet points: asymmetric structure, dynamic magnetic dominance, anomalous chemistry. But perhaps the most telling change happened in observational astronomy itself. Where researchers once strained to fit the nebula into old frameworks, they now actively searched for others like it, revisiting archival data with fresh eyes, questioning whether past oddities dismissed as instrument glitches might actually be distant cousins of this cosmic rebel. The nebula's reclassification did more than add a new entry to astronomy's taxonomy. It rewired how scientists approach anomalies. Suddenly, the outliers in every dataset became potential trailblazers rather than nuisances to be explained away. A team at MIT even developed an AI algorithm nicknamed Nebula Rebel, designed specifically to flag objects that resist categorization, turning the search for cosmic misfits into a systematic pursuit. The universe, it seemed, had been trying to show us something all along. We just needed the humility to admit our frameworks were incomplete. This shift wasn't merely academic, it had practical ramifications too. Funding agencies established new grants for non-standard nebula physics, while telescope time allocation committees prioritized observations of other candidate UMNs. The most poetic validation came when the nebula that started it all was selected as the first target for a radical new imaging technique on the James Webb Space Telescope, its chaotic beauty now deemed worthy of humanity's most advanced eyes on the sky. What made this consensus so meaningful wasn't just the acknowledgement of a new class, but what it said about science's capacity to evolve. For centuries, astronomers had sorted the cosmos into neat categories handed down from Herschel to Hubble. Now, staring at this tangled masterpiece of gas and magnetism, they'd done something far more courageous. They'd let the universe teach them a new way to see. And in that act of collective humility lay the real triumph, not just discovering something new about space, but rediscovering the boundless curiosity that makes exploration possible. The nebula's greatest gift to astronomy wasn't just a new classification, it was a masterclass in intellectual humility. Before this cosmic rebel came along, the field often treated anomalies as nuisances, data points to be smoothed over or rechecked for errors. But here was an object that refused to be ignored or explained away, its very existence demanding a radical shift in perspective. Suddenly, the outliers in every dataset became potential treasure maps rather than dead ends. Astronomers began referring to this transformation as the nebula effect, that moment when you stop asking, "What's wrong with this observation?" and start wondering, "What's right about it that we're missing?" This mindset shift rippled through research methods in subtle but profound ways. Take the case of fast radio bursts, those mysterious millisecond flashes from deep space that puzzled scientists for years. Early theories dismissed them as instrumental glitches or atmospheric phenomena, but researchers who'd wrestled with our nebula's mysteries approached them differently, treating their inexplicable patterns not as problems to solve, but as clues to a larger cosmic story. That patience paid off when some bursts were eventually linked to magnetars, revealing a previously unknown channel of extreme astrophysics. The nebula had taught them to sit with uncertainty, to let the universe reveal its secrets on its own timetable. The change extended beyond individual discoveries to the very culture of astronomy itself. Grant proposals that once prioritized safe, incremental projects now celebrated high-risk, high-reward inquiries into cosmic oddities. Peer review became more open to unconventional interpretations, recognizing that today's heresy might be tomorrow's textbook standard. Even telescope time allocation committees started reserving slots specifically for anomaly hunting, dedicated observation runs targeting objects that defied classification. The nebula's legacy lived on in these small but significant institutional shifts, proving that one stubborn cosmic cloud could redefine how an entire field approached the unknown. Perhaps most remarkably, this new flexibility began yielding dividends in unexpected places. When the Vera Rubin Observatory's legacy survey of space and time started detecting stellar ghosts, stars moving through galaxies without visible companions, astronomers didn't force them into existing categories. Instead, they drew direct parallels to our nebula's missing central engine, positing entire new classes of dark stellar remnants. Similarly, the puzzling, odd radio circles discovered in 2020 were immediately studied through the lens of morphological uniqueness rather than dismissed as artifacts. The nebula had given scientists something priceless, permission to say, "We don't know yet," without fear of professional stigma, creating space for truly groundbreaking ideas to emerge. This cultural transformation reached its zenith with the rise of adversarial collaboration in astrophysics, a method where researchers with opposing theories about an anomaly work together to design definitive tests. Inspired by the nebula debates, teams now actively seek out critics to stress-test their ideas, recognizing that intellectual friction often sparks the brightest insights. It's a far cry from the old model where competing camps would hoard data until they could present airtight cases. Today's astronomers, shaped by the nebula's lessons, understand that cosmic truth is too vast for any one perspective to grasp alone. The ultimate testament to this paradigm shift came from an unexpected source: the Hubble Space Telescope's final upgrade. Engineers added a new imaging mode specifically optimized for capturing non-standard morphologies, a direct response to the challenges posed by our nebula's tangled beauty. In that moment, the rebel that had once been called an irritating exception was immortalized in the very design of humanity's most iconic space telescope. Its greatest lesson now literally shaped how we see the universe, not as a puzzle to be solved, but as an endless frontier of wonders waiting to rewrite our understanding. The nebula's greatest legacy might not be found in research papers or telescope archives, but in the wide-eyed wonder of students who first encountered it in planetariums or late-night YouTube deep dives. Take 16-year-old Priya Gupta, who stumbled upon a documentary about the cosmic rebel while browsing science channels instead of studying for her chemistry final. The moment she saw those chaotic filaments defying classification, something clicked. "It was like the universe winked at me," she'd later tell her college interviewers, hands gesturing wildly. Here was this thing that looked like it was breaking all the rules, and instead of saying that's impossible, scientists were leaning in closer. Today, she's pursuing a PhD in magnetohydrodynamics, Her thesis focused on recreating the nebula's peculiar plasma twists in laboratory simulations. This cosmic enigma has a knack for appearing at pivotal moments in young lives. When high school teacher Carlos Mendez projected the nebula's latest Hubble image during an astronomy elective, he noticed an unusual quiet fall over his usually restless classroom. "You could see the gears turning," he recalls. One kid actually muttered, "Wait, we don't know what that is," like it had never occurred to him that the universe still held mysteries. That student now runs a popular astrophysics blog dissecting newly discovered anomalies, his tagline borrowing a line from his favorite professor. Nature's most interesting answers often begin with someone asking, "What the heck is that?" What makes the nebula such a potent inspiration isn't just its defiance of expectations, but how it embodies science's most thrilling promise. Groundbreaking discoveries aren't confined to history books. For generations, students learned about past revolutions, Galileo's telescope, Hubble's expanding universe, as if all the big revelations were behind us. This shimmering knot of gas and magnetism proves otherwise. When university outreach programs bring telescopes to underserved communities, they've learned to save the nebula for last, not just because its beauty dazzles, but because its unresolved nature makes astronomy feel alive, urgent. "You can show them Saturn's rings," says outreach coordinator Lin Yao. "But when you point to that fuzzy patch that's stumping NASA scientists, that's when hands shoot up with questions no one can fully answer yet." The ripple effects extend beyond academic tracks. At robotics competitions, teams name their creations after the nebula's features, the corkscrew jet or Europium storm. Coding boot camps use its unpredictable changes as challenges for AI pattern recognition algorithms. Even elementary school science fairs feature more unknown mystery substance experiments, a subtle shift educators attribute to children internalizing that not everything fits neat categories. The nebula has become shorthand for curiosity itself, a reminder that the most exciting words in science aren't "Eureka," but "that's weird." Perhaps most powerfully, it's reshaping what mentorship looks like. Veteran astronomers, once expected to have all the answers, now bond with Protei, gaze over shared uncertainty. Dr. Elena Park, who's guided 30 grad students through their theses, noticed a change. Before, they'd come in terrified of being wrong. Now they bring me observations that don't fit models like prized gifts. "Look what I found that breaks the rules." She keeps a framed Hubble image above her desk, not as decoration but as a teaching tool. When students get discouraged, she points to those tangled filaments. "See that? The universe is still writing its textbook. You've got time." This cultural shift reaches all the way to NASA intern programs, where applications now routinely cite the nebula as inspiration. One standout essay from a community college transfer student went viral within the agency. "You told us space was full of answers. I fell in love when I learned it's full of better questions." That sentiment, that science thrives not on definitive answers but on mysteries that pull us forward, might be the nebula's most enduring gift. It's turned generations of students from passive learners into active explorers, their eyes trained not just on known constellations, but on the dark spaces between, where the next cosmic rebel might be waiting to rewrite the rules all over again. Even now, decades after its discovery, this cosmic rebel still commands the attention of telescopes across the globe and beyond. Teams at observatories from Chile to Hawaii maintain nightly vigils, tracking subtle shifts in its chaotic filaments with the dedication of detectives on an unsolved case. The European Space Agency's Gaia mission recently contributed a game-changing dataset, precise measurements of the nebula's proper motion through the Milky Way, revealing it's not just sitting still but carving a peculiar path that defies galactic wind patterns. Meanwhile, NASA Chandra X-ray Observatory keeps uncovering new high-energy surprises, like last year's detection of fleeting X-ray sparks along the nebula's western jet, brief flashes brighter than 1,000 suns, lasting mere hours before vanishing without explanation. What makes current research so electrifying isn't just the new instruments, but how they're being used. Gone are the days of isolated observations. Today's studies weave together multi-wavelength data into living 3D models. At the University of Arizona's Cosmic Visualization Lab, astrophysicists don VR headsets to literally step inside the nebula's latest scans, examining its magnetic field lines like explorers navigating a celestial labyrinth. This immersive approach led to last month's breakthrough, the realization that the nebula's famous twisting jets aren't random, but follow a hidden fractal pattern resembling a quadruple helix. The discovery sent theorists scrambling back to their whiteboards, as no known plasma physics model predicts such orderly chaos. Citizen scientists are playing an unexpected role in this ongoing saga. When professional astronomers released 20 years of nebula images through the Zooniverse platform, amateur volunteers spotted rhythmic pulsations in certain filaments that algorithms had missed. One retired schoolteacher in Norway noticed a faint heartbeat, a region brightening precisely every 11 months, that's since become the focus of 3 peer-reviewed papers. This crowdsourced approach has proven so successful that the upcoming Vera Rubin Observatory is designing its public outreach program around real-time nebula monitoring, letting anyone with internet access hunt for changes in daily telescope uploads. The nebula's refusal to surrender its secrets has birthed entirely new observational techniques. Radio astronomers recently pioneered quantum interferometry, using entangled photons to achieve resolutions 100 times sharper than conventional arrays. Their first target, those perplexing knots in the nebula's jets where material seems to vanish, then reappear microseconds later. Early results suggest something even stranger than imagined. The knots might be natural versions of quantum erasers, regions where the fabric of spacetime itself behaves like a lab-scale double-slit experiment blown up to cosmic proportions. Perhaps most telling is how the nebula's mysteries are reshaping research priorities. Where most astronomical objects graduate from discovery to monitoring phases, this cosmic enigma keeps earning dedicated observation campaigns. The James Webb Space Telescope has already devoted 12% of its discretionary time to nebula studies, uncovering molecular complexity that makes Saturn's moon Titan look simple by comparison. Just last week, its mid-infrared instrument detected the spectral signature of vinyl cyanide in the nebula's dust clouds, a compound previously only seen in Titan's atmosphere and implicated in membrane formation for potential extraterrestrial life. The future promises even more revelations. Next year's launch of the Nancy Grace Roman Space Telescope will map the nebula's magnetic fields in unprecedented detail, while the Square-Kilometer Array's first full-scale observations aim to decode its mysterious radio pulse patterns. Back on Earth, quantum computers are being programmed to simulate the nebula's plasma dynamics at scales impossible for classical supercomputers. Early test runs have already produced bizarre magnetic geometries that match telescope observations, hinting that we might finally be developing the tools to speak this cosmic rebel's language. What keeps researchers returning to this puzzle isn't just professional curiosity, but the thrill of confronting something genuinely unknowable for now. Every time we point a new instrument at it, the nebula responds not with answers but with better questions. Its greatest lesson might be this: the universe reserves its most profound rewards not for those who seek confirmation, but for those brave enough to dwell in uncertainty, where every observation is a first step rather than a final word. The nebula that rewrote the cosmic rulebook leaves us with a humbling truth: the universe delights in defying our expectations. This tangled masterpiece of glowing filaments and rogue jets didn't just break the mold, it revealed how much we still don't understand about the forces shaping space. Think about it, every textbook description of nebulae had to be revised because one cosmic rebel refused to follow the script. Its very existence is a reminder that nature's creativity dwarfs our attempts to categorize it. Like an artist who blends every color into something entirely new, the cosmos crafted a structure that exists outside every box we've built to contain it. What makes this story so compelling isn't just the scientific breakthroughs it sparked, but how it transformed the way we approach the unknown. Before this nebula, anomalies were often sidelined as curiosities. Now they're celebrated as portals to new physics. The collaborative frenzy it inspired with radio astronomers in Chile trading data with plasma physicists in Tokyo, or graduate students spotting patterns veterans missed, proves that the greatest mysteries unite us. When was the last time a cloud of gas made headlines, fueled art exhibitions, and became a metaphor for embracing uncertainty? This nebula didn't just challenge astronomy, it became a cultural touchstone, reminding us that wonder is the engine of discovery. As we peer deeper into space with telescopes like James Webb, the nebula's legacy lingers like a cosmic whisper. Stay curious, for every mystery we solve, a dozen stranger ones emerge. Maybe that's the real gift of this unclassifiable wonder, not the answers it provided, but the better questions it taught us to ask. So here's my challenge to you: look up tonight. Somewhere in that starry expanse, another cosmic rebel might be waiting to shatter our assumptions. The universe's greatest lesson: it's always got surprises up its sleeve. Now it's your turn. Tell me in the comments, what celestial mystery keeps you staring at the sky, hungry for